Hello, welcome. In this short video, let us look at the derivation of sequential Bayesian estimates of mean and covariance of a hidden variable in a linear Gaussian model. So given the following model, yn equal to phi n multiplied by x, where x is the hidden variable, plus wn, and wn is the noise component, and phi n is obviously the linear transformation matrix. So the problem is at n equal to capital N, that is given n measurements, we know the current density of the hidden variable x as a normal distribution with mean equal to mu x of n and covariance equal to sigma x of n. Given the new measurement yn plus 1, we want to find the posterior of x given the new measurement. So by using the Bayes rule, we know that the posterior p of x given the n plus 1 measurements is equal to the current prior multiplied by the current likelihood divided by the evidence due to the latest measurement. And this derivation is given in a previous video. Please follow the link for the derivation. And since the prior and the likelihood both follow a Gaussian distribution, the posterior should also follow a Gaussian distribution because the prior and the likelihood form a conjugate pair. So the structure of the posterior PDF of x, that is p of x given y1 to n plus 1, should be equal to and should have the same structure as the product of pn of x into pyn plus 1 given x, which is proportional to exponential of minus the exponent of the prior, which is x minus mu x of n transpose sigma x of n inverse x minus mu x of n. Again, we have the likelihood of yn plus 1 given x, which is yn plus 1 minus phi n plus 1 x transpose sigma y given x inverse, and then we have yn plus 1 minus phi n plus 1 into x. So this is the structure of the posterior of x given the new measurement or given the n plus 1 measurements. And moreover, the density given y1 to n plus 1, that is n plus 1 measurements, should also follow a Gaussian distribution or a Gaussian density function which has the following exponent: x minus mu x of n plus 1 transpose sigma x of n plus 1 inverse x minus mu x of n plus 1. Now by comparing these two exponents, we can clearly see that the covariance sigma x of n plus 1 inverse is equal to sigma x of n inverse, that is the inverse of the latest covariance is equal to inverse of the previous covariance, plus that is the inverse of the covariance at n plus 1th measurement is equal to inverse of the covariance at nth measurement, plus we have phi n plus 1 transpose sigma y given x inverse the matrix phi n plus 1. So this gives the inverse of the latest covariance matrix. So this is equation 1. Now by comparing the linear terms, we can see that the product sigma x inverse n plus 1, that is sigma n plus 1, sigma x of n plus 1 inverse multiplied by mu x of n plus 1 is equal to the inverse of the previous covariance matrix multiplied by the previous mean plus phi n plus 1 transpose multiplied by the inverse of the conditional covariance matrix of the measurements multiplied by the latest measurement. Now by simply pre-multiplying with the covariance matrix n plus 1 at n plus 1, we have the latest mean vector, which is equal to the product of the covariance matrix at n plus 1 multiplied by inverse of the covariance matrix at n, that is at given n measurements, multiplied by the previous mean plus transpose of the latest transformation matrix, inverse of the conditional matrix, the conditional covariance of y, and then the latest measurement yn plus 1. So this expression gives the n plus 1th mean vector of the hidden variable or hidden variable vector x, and this expression, this one, gives the covariance structure, that is inverse of the covariance at the n plus 1th measurement. Thus, for a linear Gaussian model, we can derive the sequential Bayesian estimates of the mean covariance of the hidden variable. Thanks for watching.